Good morning, everyone, and welcome to our ESIC seminar. Today, we have a distinguished guest, Dr. Chuck Wells from PICE Incorporated in California. PICE is also a member of our ESIC Center, and Chuck is a founding member of PICE, and he has over 40 years of real-time control experience. He is a military veteran and a professional chemical and electrical engineer. Chuck has over 18 US patents. He has published 60 plus technical papers and has co-authored 2 books on advanced industrial control. He has founded many startups. So if any of you interested in startups, he's the guy
Some good lessons to learn.
Advice. And also, he's an expert in synchrophasor measurements and their applications in the power industry. And we will hear a lot about that in today's presentation. Early in his career, Chuck worked on the first versions of energy management systems for utility companies, including state estimators and advanced SCADA systems. Then he spent 20 years in developing advanced industrial real-time control systems for paper mills, steel plants, wastewater plants, nuclear reactors, metals, and mining applications. So he has a lot of experience in the industry. Then he was in Electric Power Research Institute. He worked on advanced distribution modeling and transmission power flow software. He spent several years at OSI Soft, which is where I met him, and he was at OSI Soft. Chuck patented hierarchical microgrid control systems, grid failure detection, event detection, and wide area situational awareness tools. So let us welcome Chuck.
Well, thank you all for attending. And I will have to say I was very impressed by the tour that I received and appreciate the opportunity to speak with you today and hopefully provide some ideas and innovations that will help us get to a much better electric power grid. So that's our major goal, is to come up with a solution that will allow us to have maximum amount of renewable power into the grid with minimum investment, maintaining resiliency and stability of the grid. So what we're going to talk about today is our approach to doing that using collections of microgrids. And I think from most of you probably believe this is also the optimal solution to the grid is to implement first a baseline controller, microgrid controller, and then build control systems on top of that baseline controller. Today, we're having some major issues with stability in the grid. Some recent publications by Dominion Energy showed a substantial increase in oscillations at 11 hertz. This is higher than what I've seen the research in the WSU is looking at lower frequency oscillations. How do we control 11 hertz? And where's the 11 hertz coming from? More than likely, it's coming from uncoordinated implementations of inverter-based solutions. These are likely to be the cause. We don't know that for sure, but it also can be due to the fact that we're losing inertia in the grid. The grid then is more sensitive to disturbances. The disturbances are coming from uncontrolled DERs. They're causing the RLC part of the grid to be more predominant than it is today. When it's massively damped by large generation, we don't see this higher frequency oscillation. So these harmonic frequencies are probably going to get more important in the grid. So we need to find a solution for them. We also are facing some problems with industry. The industry is trying to solve this problem, in my opinion, by adding artificial inertia to their existing grid following inverters. That is, from my perspective, from a control engineering perspective, that is the wrong approach. We need to have inverters that are, first of all, voltage source inverters, and second of all, they need to respond very fast to commands. You may or may not be aware that most commercial inverters today only speak Modbus protocol. Modbus protocol really has no limits on the speed, but in fact, because of limitations in the network communications, the fact there has to be an acknowledgement come back from every command slows it down. So the best we can do today is 5 hertz control. Our position is we need 60 hertz control at the inverter level. So I tell it to go to 10. I want it to get there, in 16 milliseconds. That's not happening today. And finally, we also have a problem of how do we control millions of inverters? The industry today is thinking of a non-scalable solution. They're thinking of, I need to build a software package that will control 1 million DERs. That is not the right approach. We need to build a software solution that will control maybe 10 to 50, and then form a hierarchy of identical controllers. And we'll talk about that in just a minute. So the industry is pushing very hard to provide artificial inertia, and it's causing trouble for our company. I have several examples where I could not achieve the objective that the company that we promised to the utility because the inverter manufacturer will not allow us direct control. We have to send an indirect control. And of course, the other issue is how do we provide resilience to weather-related problems? I believe, probably most of you younger people also believe, that we are really close to the tipping point. We need to come up with a solution to remove carbon from the atmosphere. One way to do that is to go maximum amount of renewable into the grid. So we need to find a solution that will allow us to handle these weather-related problems by using microgrids to provide this resilience to weather-related problems. Okay, so I'm going to just summarize what we're going to talk about for the rest of the 40 minutes. I want to leave some time for questions because the questions I've gotten so far in the tour have been quite good, and maybe I'll get some more innovation. We think that this fast control is needed, and we're an advocate of 60 hertz control. We need to find a way to provide incentives for people to install microgrids. They're going to call it, all I want's a PV in my house and a battery. Well, a PV in your battery really becomes a microgrid. So in order to allow you to have control of that resource, we want to use the existing infrastructure more efficiently. There are multiple people who believe that the infrastructure we have is sufficient. We just need to use it more efficiently. We don't have to build transmission lines. We need to put the generation where the load is, not out in the desert, and build new transmission lines. So that's our thought also. Let's use the infrastructure that we currently have. And finally, we have to get over this grid forming inverter problem. The industry is totally rejecting the idea of grid forming inverters in microgrids. They insist on everybody being a grid following, and in particular, the diesel generator being the lead grid forming device in a microgrid. We don't want the diesel generator to run at all. Unless there's an extended outage, then the diesel generator runs. This is a quick definition of a microgrid from the DOE. The key word here is single controllable entity. Single controllable entity. That means any point in the grid where I have the ability at a single point to control the flow. That can be a POI. They call it a POI. That's a point of interconnection to the grid where I control the flow, and that doesn't have to be a residence, a commercial building. It can be any point in the grid where all the power will flow through that point with no other uncontrollable sources. Now, there are going to be some session. Professor Manning has some ideas about how to solve that problem. But basically, a hierarchy where at the POI, all power flows. I want to be able to control that. So here's a typical solution. It needs the following things to work. It has to have the ability to communicate reliably. And I believe there's a new protocol. It's called IEEE 2664. It's going to be a standard this year. It's called Streaming Telemetry Transport Protocol. It has low dropout rate, low latency. It's secure, goes through the internet. So if you're far away and you need to communicate to a DER, use this protocol. I mentioned fast feedback. I mentioned hierarchy. Now, modular microgrids is another problem. The industry today is not producing modular microgrids. They're all different. They're all private, specialized, yearly or 2 years or 3-year projects to install a microgrid, because the designer and developer of the microgrid, he wants inverter A, he wants battery B, he wants solar C, he wants load control devices E, and so forth. None of them speak a common language. So it's the spaghetti approach. You have to write an interface from every device to every other device. That's no good. That's not going to work. We mentioned grid forming inverters. And finally, time synchronized devices. This is extremely important in control, to use time synchronized measurements. The reason being, when we do a control calculation, as you all know, you get a measurement, you have a set point, you calculate the error. Your set point value and your measurement should be at the same time. In a SCADA system, they can be off by 4 or 5 seconds or 15 seconds. Actually, in a microgrid system, we've seen 15-second delay in a traditional microgrid system, and that's due to the way the switches are located, the way the network is structured, the number of RTUs that are installed, number of PLCs that are installed that we have to get data from. So if there's a lot of extra devices in the network, you get added delay. And I can tell you, in a 60 hertz control system, I get 15 seconds of pure time delay. Why? Because of poor design of the communication infrastructure. We can overcome that problem. So this is the summary of what I'm going to talk about. This is an example of beginnings of a modular microgrid. This was installed in 2016 in Sempra headquarters. You basically put all the stuff in a box, put it on a truck, ship it to the site. This is on the 3rd floor of a parking lot in Sempra headquarters. Take it up to the 3rd floor with a crane, drop it in, plug it in, and now you have a microgrid. And this microgrid saves $7,000 a month on your power. So it's a good investment for people to think about modular microgrids. Now, it took us, I'd say total of about 6 months to get this software to work, because this is the first one we did. Now, I want to give you another example of an analogy. This is quick also, but some people don't fully get the idea of flow control at the POI. So in this particular case, we're talking about at the POI, I want to control the flow. How many gallons per minute of water am I contracted to either buy or sell? Well, I have an uncontrollable source of water. I have uncontrollable loads. I have controllable loads. I want to build a controller that will control the flow. Now, I put kVARs, H's, and kWatt H's. Now, this is to show you the analogy. There's no such thing really of a kVAR H in a battery. You have to create the VAR H from the battery. But the idea is that in the storage system, you have the ability to create real energy and reactive energy. And so this just shows you that analogy. Now, this is how we see the microgrids being operated. You have a 480 volt connection to a meter. That's the single controllable entity. You have uncontrollable loads behind this device. And our goal is to control the flow at that point of interconnection. Now, when I say control, what type of control are we talking about? And also, what kind of measurements are we talking about? At that point of interconnection, we're talking about the voltage magnitude and the voltage angle, the current magnitude and the current angle, and the frequency. That's all I need to do control of real and reactive power. I'll compute the real and reactive power from these raw measurements. Now, I can also get the measurements directly from a relay through the IEEE standard C37118, which is typically known as a PMU. Now, we've mentioned that we have to control the flow. We have to optimize the flow because why would people buy a microgrid in the first place? They want to reduce their power bill or make money. That means they have to have an optimizer. So a microgrid needs a built-in optimizer to figure out if I am participating in the market, what am I going to bid into the market in terms of P&Q at a specific time and keep my battery full. Because if my battery runs out, I've lost control authority. That's another thing that a lot of people sort of ignore. How do you control the battery profile to allow you to get optimal control of the POI at the flow point, at the point of interconnection? So this summarizes it. If I'm in connected mode, I want to be able to minimize my cost of energy. And that's typically done by calculating the optimal POI real power flow at the point of interconnection to minimize my demand charge. And in California, we have very high demand charges, $45 per kilowatt. That's a lot to pay per month if you exceed a limit. So you need to control demand. And we also have high time of use charges. So you want to shift the load consumption, shift your import as far as possible to the minimum time of use zone. And of course, you also have to figure out how big your battery should be to do that. So that's the main objective. But also to provide incentives for the customer, you need to be able to have a system that will allow you to provide local services to the grid from your POI. For example, a utility may have signed a contract with you that said, I want you to allow me to regulate your POI from noon until 3 o'clock in the afternoon any way that I want to maintain stability of the grid, and I'll pay you X number of dollars if I take control of your POI. The utility will compensate you for doing that. The other thing, of course, I mentioned is you can participate in energy trading. You can participate in with a local marketplace and say, I'm willing to sell you my power because I have excess power from 1 o'clock until 4 o'clock in the afternoon. I'm willing to sell you this at 40 cents a kilowatt hour. And in which case you'll get a dispatch, a remote signal from the utility or from the marketplace saying, go to your bid value right now and stay there until I give you another set point change. There's two other applications. One is oscillation damping. If the control system is able to respond fast, by control system, I mean the microgrid itself, the microgrid set point. If I'm able to give the microgrid set point a change of P and Q simultaneously, I can then dampen the oscillations of the grid. And as you learned in your Control 101 class, you can calculate what the tuning coefficients are to cut off all frequencies lower than that number. That's how we tune the controller as an oscillation damper. And the last one is the FLISR, the fault location isolation system restoration. This is where we detect a fault in the grid and we disconnect ourselves. We would say, I'm going to get off the grid because I'm paid to do that now by the utility. I'm paid to disconnect and run as long as I can. I'm going to tell the utility how long I can run in the disconnected mode. But I'm going to disconnect and I'm going to give information to the utility to decide what other microgrids should be disconnected to maintain stability of the network and to maximize the number of customer loads that are served. So utility wants to serve maximum number of loads. That makes maximum amount of money. So they want to disconnect the minimum number of guys to keep the grid stable, because if they don't disconnect them, the rest of the grid is going to collapse and they're going to lose a lot of revenue. So it's purely a greedy solution. Now in island mode, I want to be able to solve a different objective function. I want to be able to maximize the time to live typically. And finally, I want to be able to, when I do disconnect and reconnect, I want to do that seamlessly. That's another issue that you'll see in the literature. For example, Duke Power recently released a brand new top of the state-of-the-art microgrid controller. It only takes 30 seconds to black start to reconnect. Okay, that's really not in the definition of microgrids from the IEEE. You need to be able to seamlessly connect, seamlessly disconnect. Now, I'll explain one way to do that. This is just a quick summary of what we mean by the closed loop response of the microgrid. By the way, this is right out of the IEEE standard 2030.8, the testing standards. Typically, ERCOT, for example, if you want to participate in the fast frequency response at ERCOT, you have to show that you can do a set point change in 250 milliseconds. That's faster than, I mean, it's slower than 4 cycles, but I think we can make a 4-cycle one as well. Faster is better in the electric power grid, is our thesis. So basically, we want the closed loop control system to be able to have a response like this. Now, most people in the power industry are not used to feedback control systems. They're used to open loop control, droop control, for example. Oh, when the frequency gets to this, I go to that. Okay, that is some form of feedback, proportional feedback. But in our opinion, the feedback control system that is needed to achieve this kind of response is at least a PID type of controller. You need the integral to get to 0, set point. You need the derivative to get you there fast and slow you down as you approach the set point. And you need the proportional to figure out how much you're going to need. So this is the basic concept. Now, we've already discussed why fast control systems are needed. I wanted to go on to show you some other data. This is from Dominion Energy. They showed this at one of the NASPE meetings in March. I was totally shocked by this. I had only seen the oscillations that Manny typically shows us, under 1 hertz oscillations in a large power grid. This is 11 hertz. How are we going to control 11 hertz? According to Nyquist, we better control then at 22 hertz. Why not just go all the way to 60 control and let's control at 60 hertz? And now we can dampen these frequencies. Now, the question is, and Dominion Power did not tell us where they are coming from because they didn't know. But our conjecture is that this is due to, as I said earlier, loss of inertia in the grid and interaction of uncontrolled DERs. Now, we have come up with this sort of idea. Manny and I worked on this a few months ago. It's a concept of a hierarchical control of microgrids. Now, it's a strict hierarchy, but I believe there's some flexibility here to make it so it doesn't have to be strict. It could be that peer-to-peer is allowed. Peer-to-peer communications requires more mathematics to solve than a pure hierarchy. We're thinking initially, let's take a baby step. Let's go to a pure hierarchy, no peer-to-peer communication, only parent-child communication. And the other concept is that these microgrids do not have to be associated with hardware. They can be virtual microgrids. Any point in the grid, here's one here. There's no switch and no meter here, but I can estimate what the real and reactive power flow are at that point and use an estimate of the grid. And you all know in power systems that we've been doing state estimators for a long time, and we know how to do them. We know also how to do them better with phasor measurements. So our concept is that even if you don't have a measurement, you can still do control using the estimated variable as long as you have confidence in your model. And I noticed in one of the labs Manny has, when he talks about oscillations detection, he talks about confidence. How confident am I that this is an oscillation that's serious enough to cause an alarm? We need to have confidence in the model. And so that requires data, that requires some more advanced technology than we've implemented today. but we need to have continuous validation of the network flow model because we're going to use that to continually tune and use it to determine which of these microgrids should be automatically islanded. You guys probably already know this, but why is a 2x2 controller needed? They're not used in the industry. We use very few single loop controls. You know, we use volt var control, we use frequency watt control. Those are not even real feedback control systems. Those are open loop scheduled systems using a proportional slope. Well, all 2x2 control systems are used extensively in other industries. The biggest example, or the most well-known example, is a paper machine. I spent 20 years in paper machine business using 2x2 controllers. What are the 2x2 controls? There's basis weight and moisture on the sheet. And then 2 minutes earlier, there is a flow signal and a steam signal. So steam flow and fiber flow put on a wire. You wait 3 minutes and you get a basis weight and measurement, basis weight and moisture. How are we going to control a system that has a 3-minute time delay? Well, we know how to do that with time compensated controllers. So most of these are called Smith predictors. I think you probably studied Smith predictor. But let's take a 2x2 controller, and we have P and Q as the inputs, the output of the system. But guess what? In a power system, we have some other stuff that affects the P and Q. We have the individual angles of the voltage itself and the current itself. We have the angle difference between the voltage and the current, and we have the magnitudes. So truly, an electric power system, in my opinion, is a 2-input, 2-output system, 2 inputs that are controllable. This is another simple example. What we're trying to control here is the real and reactive power on the right-hand side of that circuit. You know, by controlling, what are we going to control? We're going to control the angle, we can control the voltages to get the flow that we want, the flow and the real and reactive power flow that we want at the receiving end. So this is why we are strongly urging industry to adopt a 2x2 decoupled controller with time delay compensation. As I mentioned earlier, I have a 15-second time delay in a control loop. Thank God I knew how to control paper machines because this is like a fast paper machine. So I know how to control this now. Now, this is an example of the controller we have implemented. It does have a decoupling gain matrix shown there in the middle. It has a PID, 2 PID loops. Now, it has the Smith predictor time delay compensation, which is sometimes used and sometimes not. The key here, one of the keys in this controller is this derivative term is not off of the error. Every PID controller in the world today calculates the derivative off of the error signal. That's wrong, because if you do a set point change, the error signal is going to have a delta. It's going to have an impulse function, almost an impulse, and that's going to cause the derivative action to go nuts. So you don't want that. You want the derivative action on the measured value. So we call it the PIFD, proportional integral filtered derivative. So this is implemented in the control system. This is a simplified block diagram. We also want to show feed forward because when you must have a feed forward term if you're going to have an unplanned disconnect from the grid. Say you're pulling 10 megawatts and you get a sudden drop. What do? You better send a 10 megawatt signal to your battery right now. Otherwise, you're going to lose the load inside. So you must have feed forward control for unplanned disconnect. Now, if it's a planned disconnect, then we simply ramp the flow down to 0 and disconnect, and there's no need for a feed forward signal. That's the reason for the feed forward action. Now, I wanted to summarize what we think a standard microgrid is. There should be one piece of software that is the microgrid controller. That piece of software should be configurable so it will control a number of inverters, a number of batteries, a number of PV generators, a number of uncontrolled loads. It cannot send any commands to a controllable device that will cause a network exceedance. Otherwise, the owner is going to get upset because you tripped off some equipment because you sent too big a P command to an inverter. So every command that's sent needs to be checked for thermal and voltage constraints inside this microgrid. Now, some microgrids only have one battery, but some have multiple batteries, and some have multiple DERs, some have multiple generators. So the software needs to be written in a way so it can have an arbitrary number of these. Now, our software is currently set up to these parameters. I think we'll probably keep it that way. Now, this brings up another issue of what kind of controller can you buy from an RTU vendor that will control this number of devices at 60 hertz? There are none. Because the control manufacturers are using software that was developed in the 1970s. I'm not kidding you. Modicon was the first PLC developed in 1979, and it used ladder logic. So now you have to code each line of code. There's no subroutines, no functions. Each line of code. It's almost like visual, not like basics, but anyway, there's no subroutines in the code. There's now structured text that is helpful, but you still have to do block coding for your microgrid. So now you have to program 50 blocks if you have 50 DERs. Wouldn't it be nice if you just have to write the number 50 and say, now I have 50 of these devices? So that's what we recognized when we started PICE. We need a new generation of PLCs that don't use the 70-year-old, 50-year-old PLC analogy of how to write software. We wrote the software one time in C, and it's driven off of a database, and it's configured. So the field engineers, they don't know what's underneath. They just know it runs at 60 hertz, and I can configure it through an Excel spreadsheet, and now my control system's working. That's in theory. It doesn't always work that way. Now, the issue of two other issues I want to mention, and I want to stay aware of time here because I would like to get your questions. The issue of connection and disconnection. I mentioned how you disconnect fast, disconnect slow. How do you reconnect? That's somewhat of a tricky problem. Why do we need a PMU at the point of interconnection? We need the PMU to match the angle of the islanded grid with the angle of the main grid to within 10 degrees, according to the IEEE 1547 standard. That relay will not close unless your angle is within 10 degrees. That's settable between 10 and 30 degrees, I believe, depending on the size of the microgrid. But in any event, so that it raises the issue. How do we control? By the way, when you're in microgrid mode, your inverter is in voltage source mode. That means I can send frequency signals and voltage signals to the inverter. Now, I'm not going to send it a voltage signal because the voltage is where I want it to be. But I'm going to give it a little bump in frequency from 60.000 to 60.050. What's that going to happen? The angle is going to change at 18 degrees per second until I get to the real power that I'm asking for. Also, that angle is going to change to the angle of the main grid. Why don't I put a simple PID controller on the angle of the main grid and a set point of 0? I want those two angles to equal. and I put it in a fast feedback loop that drives the frequency signal of the inverter until I get the frequency that I'm within 10 degrees, and then the system will close. The relay will close, bam. So that's an angle tracking feature. Now, here's something that's also interesting, and Manny and I have talked about this for about 20 years also. This could lead to more sophisticated control by controlling the angle and the voltage. The state. Notice nobody's talking about state variable control in microgrids. State variable control is talked about theoretically in transmission. Very little is done in terms of control of state. We need state variable control all the way down to the POI of the microgrid. Now, I think in the next 100 years, probably that will happen. I won't be around here, but I've been pushing it since 1968. It's a way to control the grid as a state variable system, but I have not had any success whatsoever. However, I slipped in a state variable controller because I am now actively controlling the angle of my microgrid to track the angle of the main grid. And it works like a charm. When I tell that thing to connect, bam, it'll connect immediately. If you talk to other people and they tell it to connect, it may or may not connect, depending on what the angle difference is. And eventually the angles may get close enough, and then the relay will close. But I was involved in the University of San Diego blackout. They never got it to close. 2 days in island mode on backup generators before they could connect to the grid, and then they had to shut down the whole campus. Black started. Could never get the angle close, because if the grid angle is moving around at one speed and the microgrid angle is running at a different speed, they may never close. They get close, they'll go like this, but you got to get them to go like this for it to cross, and then they will close. 2 days, UCSD never closed. Okay. Now, just a few minutes on network modeling. All of you are familiar with network modeling. I believe that a 3-phase network flow program is required. It should run inside the microgrid. Doesn't have to be a big one. It can run just very fast. It can run at 1-second intervals and solve the load flows from within the microgrid controller, so that when the next dispatch is made, you can check the model to see, will this P cause a thermal or voltage constraint anywhere on my network? Now, there's some very clever stuff that can be done, I think, with having the controller and the model together. And when you optimize, you use the network model as a constraint. We don't do that. But all of your classes in control and optimization theory talk about, you write the objective function subject to constraints. The constraints should be the network flow model. We don't do that. We sort of do it after the fact and hope that we don't hit a constraint. But the optimization should be done subject to a network flow model. That's something for the future. Now, I want to talk just a little bit about the optimizer. I can't talk too much about it because it's stuff that we have not patented. We haven't disclosed to anybody how we actually do it. But we built in our own optimizer that basically lets the user specify the objective function, the equality constraints, and the inequality constraints. And we solve that every 5 minutes for the optimal flow of the real power at the POI and the flow of the battery and the flow of the SOC, not the flow, but the value of the state of charge of the battery over the next 24 hours. So now we solve that for 24 hours, but we only issue command for the next 5 minutes. Why do we only do that? Well, it's the standard MPC approach. You do the whole optimization, you execute now, and then you wait 5 minutes and you execute the optimization again, because your forecast can change. Now, that's another issue. What kind of forecast are we talking about? We're talking about the net load forecast. Where do we get the net load forecast? We have to have a weather forecast. Plus, we have to have historical data. There's a lot of very interesting things that I think can be done in computing net loads. more optimally. We do it pretty traditional way, 1955 Box and Jenkins technology, so we could use maybe AI approach or anyway, we know there's better ways to do it, but we use sort of a traditional approach to forecasting. Now, there's one other thing I want to mention. I wanted to mention the term dynamic operating envelope. This is mandatory in Australia. It's not never been heard of in America. Dynamic operating envelopes, I think, are very important. What they do is they allow an individual microgrid to do its own estimation of what its operating envelope can be over the next 24 hours without it violating any of its constraints. Now, that operating envelope can be given to its parent and say, here's my operating envelope. Please give me some operating instructions over the next 24 hours that are within this operating envelope. Now, this is sort of breaking the optimization problem into two parts, where you're solving a local optimization operating envelope problem, and now these becomes constraints for the parent. That's the way we see these working. We've done some partial work on that in Australia that looks pretty good. Here's an example of, this is a real quick example. This is showing the next day profile. This is how much it costs if you do nothing. You are given the battery size, the inverter size. You're given ramp rates on the battery. You're given a time of use. You're given a demand charge. You're also given what is your worst POI peak for the last billing cycle. And then you compute then the power profile over the next 24 hours for both the SOC of the battery and the POI at the point of interconnection. This is done, as I said, every 5 minutes, and it's important, obviously, that the optimization completes it in 5 minutes. Now, we run on little SEL 3355 computers, so we have to be aware of the SEL computer is not only is it doing real-time control 60 times a second, but it's also solving this optimization problem. So we are acutely aware that we may have not enough computing cycles, and so we're aware of this, and we're doing some research on ways to speed this up and to use some maybe improved optimization algorithms. And I'm certain from what I've seen, you guys are already doing that. So let's keep that up. This is the result. We're only saving about 10% here, but this gives you the optimal profile for the day ahead. Now, one more thing I want to talk about is the operating modes of a microgrid are changing. You're not always just controlling real and reactive power. Customer may have some additional constraints, or they don't want to control the P&Q. They want to smooth the power from their solar power plant. That's all they care about. They want to hold the real power at a constant. They want to hold frequency constant. They have a 200 megawatt. By the way, a microgrid doesn't matter what size it is. We use the same software where it's 50 kilowatt. We have the largest one is a 300 megawatt solar plant. It's all a microgrid as far as we're concerned. The customers don't think that. They think we have a power plant control system. We don't have a power plant control system. We have a microgrid control system. They think we have a DERMS. We have a microgrid control system. So anyway, these are the different functions that we've implemented. Now, the last one, called frequency watch, we've implemented that in Guam. That has saved them innumerable amount of outages due to under-frequency relay trips. Frequency watch is simply when the frequency gets out of bounds, you blast it with the microgrid to arrest that sudden descent. The DFDT, it comes down real fast. The quicker you can hit the grid with real power, the slower that you're going to hit that, and it won't hit the trip point on frequency. So we have got some very good results on using this frequency watch. And we've now proposed, we have 3 systems in Guam already. These are all pretty large ones. All of them are over 50 megawatts. They want to install all microgrids in Guam, and all of them have frequency watch. So that's something interesting also. If everybody has frequency watch, on their microgrid, then when you get an event, it operates like a traditional droop control. It acts right now to inject or withhold pull power. You know, if it's over frequency, you do the same. I've mentioned frequency control and so forth. I'm not going to go through this because this looks extremely complicated. It sort of is extremely complicated, but you know, every DCS system I've worked with in the past years has a faceplate. And a faceplate shows you the set point, the value, status is it auto manual, remote or control. This is our first draft. By the way, this is pretty old. This is our first idea of a standard faceplate. We do use these in all of our systems, and it does take an operator a few minutes to get used to what mode does he want to run in, what is the current status. The screens allow you to pan and zoom it back and forth. This is another example of, especially when you're deciding what state of the system you want it to be in. I know it's sort of hard to see, but I just wanted to show you that there is software. Now, one last item, and that is voltage source inverters. It's a big problem in the industry. Industry is totally resistant to this. They want all microgrids to every microgrid in island mode. These guys form the grid, the diesel generators. I don't care what else you say, the diesel generators always form the grid. These inverters are all grid following inverters. We want to change that paradigm so that these guys are always in grid forming mode. These guys are off most of the time, and when they come on, they become grid followers. They were in ESIC mode. This can be done with a simple two-level controller. Remember, I said all the control software is the same. This is a PQ controller, and it's sending VF commands. This is a P controller sending VF commands. Now, what happens when you're sending VF to a grid forming inverter? What's going to happen? Well, it's going to cause real and reactive power to flow. As soon as the real and reactive power get to the set point, the error signal is 0, and the voltage stays at its nominal voltage set point, the frequency goes to its nominal frequency, 60 hertz. If my frequency here is at 60 hertz, guess what? My angle is constant. That means the angle difference between here and here is constant. That means the flow here is constant. So I have achieved my objective of controlling the flow at this point with the same controller that I use here and there and all the way up the grid. One piece of software that does everything we just talked about. It's a big chunk of software, but you know, I know you guys don't know this, but I'm used to 16K core systems. You can't even write one branch of the letter A with 16K of core today. So I can't even tell you how big the software, but it's in gigabytes of executable binary code. But the computers have plenty of memory, so we just put one controller, two controllers, three controllers, and now we have a system that will allow us to control the POI of the microgrid. And then this has a hierarchy. And another analogy that we're thinking, we're getting a zero response in this also. Let's suppose this is a true island. It's not connected to the grid. We found in large number of sites, they have a time problem. The customers call up, hey, my clock on my refrigerator is 2 minutes off. What gives? So that we can solve the time problem by controlling, if this is a pure island, controlling this bus angle to 0 using the PMU. We just set the bus set point angle to 0. Now we have state variable control. So now we control the voltage and the angle at this point, and guess what? The clock stays at GPS time. And Manny has a very clever way of doing this with a thing called a rock that we can use to do this. We also have another approach. But in any event, we control the angle here 0. And now the time clock is always GPS time, assuming that you have synchronized your real clocks to GPS time at some time. Okay. Okay, we're sort of running out of time. I'm going to skip some of this stuff. It's the end. So I wanted to leave time for some questions because I got some good feedback from the lab visitors, and so now's the time.
Thank you. Questions?
I have a couple.
Yeah.
So you said the 3355 is sending commands on a 60 hertz rate or so. What communication protocol is that? Do you know?
The analog output signals. That's the only way we can do that.
Yeah. Okay. And then
through an RTAC.
Yeah. Okay. And then is frequency watch. So you said that if the grid's frequency goes down and then you use the microgrids to push it up, is that the same thing of what you just showed of having everything on basically frequency control? So it just knows to do it?
That's a good question, but it's not the same, because you can think of the frequency watch as a supervisory controller on the microgrid, because the microgrid is really controlling real and reactive power.
Mm-hmm.
That's its daily use.
Nice.
As an exception, then the frequency watch overrides that and gives the delta command to save the grid.
So it's okay. So it overrides because I see, because the loop is looking at P and Q, which alters the frequency and the voltage, but it skips that and allows.
It's a separate loop.
It's a totally separate loop. A totally separate
I
loop.
have a question, follow-up question on that. Say you have 10 or 20 of these devices, each starts pouring energy into the grid. Then from under frequency,
You go to over frequency. Well, that's an excellent question too,
That was my
because there is this goes back to droop control. So the frequency watch quits when you get in the deadband.
I see.
And that will prevent the over frequency problem.
Okay.
Because it would be less of a problem when we don't have as much in renewables, but if we had an overcapacity, like if our renewables could supply everything, then this would cause that
It's a big problem if we don't do that.
Yeah, because right now we don't have enough to really.
We don't have, it's not going to affect.
It'll get there.
That's why Guam has said to us, all new microgrids must have frequency watch, and they all have to work all the time. So that means we have to be careful of oscillation, of forcing an over frequency and under frequency.
And they could almost play tennis and bat each other back and forth, like this grid over here and this grid could.
Yeah, one keeps absorbing, one keeps pumping.
Yeah. So this is an interesting problem that Professor Raymond DeCalifon, he's the co-founder of PICE also. I work with him every day effectively, and he's a very good control engineer. And he has done some stuff with the frequency watch that I think is pretty clever. He leaves out integral, actually. He only used derivative and proportional. And I question us, why do you want to do that? Well, I don't want that error to be 0. I just want it to float.
Okay.
I want it to float in the deadband.
Yeah, that's a wise thing to do.
Yeah, so
You had a question.
Yeah, I actually have 2 questions. The first one is a very short one. So you mentioned that right now that you are pushing the narrative for the inverters to be always on grid forming mode, and when the DG comes up, it has to be following the voltage. So I kind of confused as to how that is possible, because the conventional way is that the DG is always the grid forming, while even if you have grid forming inverters, once the DG is there, they have to just follow the voltage and frequency of the DG. So how do we do the opposite one? That's the first question. And the second one is kind of a very long one. So you mentioned something about islanding, and I think right now most of the protection companies, when there is a fault and you want to disconnect at the POI, think that the fastest protection element that they have right now is the fast DFDT, the fast rock off. So, but in the case where the import is low, then definitely the fast rock off or the fast DFDT would not actually do the work of opening the breaker at the POI. Because if the import is low, then there won't be a sudden change of a sudden transfer of load to the local DG. So in that case, how do you actually open because it's a major requirement, right?
Yeah.
Once there's a fault, you have to open up the POI.
So maybe you can react to the first question, and then we can get to the second one.
For the first question, the diesel generators are the governor can be set to operate isynchronously. So it will follow the frequency with a PQ command. So it's like PQ command of the diesel generator in isynchronous mode. That diesel generator will speed up and slow down to hold P and Q at the set point you're giving them. So that's how we would see the diesel generator comes on. Now, I would also add that I believe that when the diesel generator is called, it should only come on at its minimal heat rate. Right now, we don't do that. We bring them on, let them cook for 30 minutes or half an hour at minimal rate, and then very slowly ramp them up to some set point that the operator normally puts in. Our feeling is that's the wrong approach. Bring them up as quickly as possible to their optimal heat rate and only run them as a base load, a base generation, and let the battery then do all the manipulation to satisfy the load. That way we burn the least amount of carbon. That's our thought on number one.
And on two, on the protection.
Now on the protection, I'm not sure I can fully answer your question, but I get this question all the time about protection of microgrids. There are every SEL relay we work with has group protection settings. So when we're in grid connected mode, we have one set of settings for protection. And then as soon as we transition to microgrid mode, we do change the group to a new setting of parameters to handle the case of much lower fault current in the microgrid. And that seems to satisfy that question. But I'm not quite sure I answered your question with that.
Okay. This is a very specific one. It's asking about the ROCA. Yeah, go ahead.
Yeah, so the summary of the question is that normally if let's say the load in the microgrid is consuming 1 megawatt, right? And the generators in the microgrid are even 500 kilowatts and you are importing 500 kilowatts. In that case, the import is tangibly high. And when there's a fault at the upstream, like if there's a fault
on the main grid,
and the recloser at the substation opens up, definitely the law says that your own breaker at the POI should also open up so that you are not backfeeding the load.
Exactly.
Yeah. So, but the relay on the POI actually opens up using the fast rock-off or the rock-off.
Right.
But the rock-off can only work if the import is if there's a high load being imported, because once there's a fault and the recloser opens up, then load that is being imported needs to be transferred to the DG in the microgrid, and that sudden transfer of load would definitely affect the frequency, and that is how the relay at the breaker would open up. But if the import is so low that you are not having like a sudden transfer of load to the DG, then the frequency will not be affected. So how do you trip the breaker at that POI without, if there is no change in the frequency, if the DFDT is not changing?
Okay.
How do you trip?
Yeah, I think I understand the question. So,
Okay.
yeah, I think this is very specific. He's asking about the mechanism of the relay, how it will react for this scenario. And I would suggest, you can say that you have your own way of disconnecting the microgrid under such situations. That's what I understood from.
I mean, what he
presentation.
basically is saying that islanding detection.
Yeah, something
Yeah,
like
You
that.
mentioned something about.
What you are saying that,
islanding.
yeah.
Yeah,
to
I think
get
with
bands-
PMUs, it becomes easier. So you can do that possibly by tracking the local frequency versus the grid frequency. And when they start to pull apart, but again, how long it will take, how quickly you can realize this, those are all the questions. That will depend on the specific algorithm that they are using.
Okay.
And I think in this case, I'm not sure if it is open or it's proprietary. So I don't want to put check on the spot to answer something that he doesn't want to.
Okay.
It's a very good question.
It is,
Possibly, yeah.
And I'm not sure I have a very good answer, but I do know that the basic philosophy is that because of we have the accurate measurement of the angle and the frequency at the POI. That gives us the ability to be smart the way we interact with the main grid. And we're smart when we reconnect because we're tracking, and that's a smooth.
He's asking about islanding.
We're talking about the other way.
Yes.
We're coming back the
Yeah,
other way.
Yeah.
The other way, what we have implemented so far is the delta loss of real power is fed forward to the battery inverter, direct. It doesn't go through the PO. And you remember I showed you the loop of the feed forward control around the control. There's no controller lag, no controller calculation of error. Boom. The delta P goes directly to the battery inverter.
Also, what you are basically saying that basically is pointing out the passive islanding detection method.
Yeah.
So therefore, when you want to use that, if you really want, you should go to active islanding detection method. Otherwise,
Yeah, that's-
always you have this issue. So there is no paper or any algorithm that 100% can
And-
detect that.
Yeah, exactly. So I understand you have something that you use to decide when to island. Maybe you didn't describe that fully here. And you may be able to follow up with, on what you can disclose.
Right.
If you have some papers or some presentation on, because you mentioned that when you think the grid is in trouble or grid is causing trouble, you can island yourself. That's what he's
Yes.
asking. How can you do that?
With
And so-
the angle difference.
Okay, so that goes back to the PMU.
PMU.
Yeah.
See, the PMUs give it's interesting. The relays that we used are the SEL relays, 351A. They give you the VS angle. That's on the grid side.
Vector shift.
And then they give us the VA, the angle of VA, BC. So if the angle VA, departs suddenly, that means you've had an event on the grid that you better get off right now. And that's when you give the delta, the delta
So
P.
that would be more an active control, the active islanding.
Yeah, that's the,
So following up on that thing, so I don't get for grid connection or for synchronization to the grid, why do you need to have a PMU? Why not just use the conventional synchronous check relays?
Oh, okay, yeah.
okay. That's what all the other competitors do. Why do you need that? You need it because you have an angle of the grid that's moving typically slowly.
Yeah, the problem is the microgrid angle, the frequency changes so fast.
Yes.
But they are at the same, so you're saying that the issue is the accuracy of the
No,
measure?
you can't keep up. It's difficult to bring it to, you can explain it better.
Yeah, I can best draw a picture of.
And maybe, are there other questions? I know, okay. Because I know our lunch is waiting as well.
This is the grid. And this is the angle of the microgrid. I have to drive this angle to within a bandwidth of the main grid angle. So I do that with delta F commands to the grid forming inverter. And that will drive this up here. Now, this is an interesting control loop that Raymond and I also had debates about. How do you do this? This one has to have integral action in it because I've got to get within a deadband. I can't have an offset. If I have proportional only control, it may just go up here and hang here. I've got to have a pure integral action in this controller to drive it within this deadband. Then I can connect. Then the relay will connect automatically for me. But if you
So
don't
again,
have,
the synchro check approach is like a passive approach. What they are doing is an active approach.
You know what I'm saying, because usually when you have PMU, the point, if it is the matter of the GPS synchronization, is when you take the measurement from two different locations. But if you're measuring the measurement from the two sides of the breaker that you connect to the grid, so why do we even, I need to have, these are already synchronized in the same device.
Oh, I see the question. What he is asking is, do you really need a PMU?
Yeah.
Because technically, all you care about is the angle difference.
the angle difference,
And
right?
you can set it as a control objective
Exactly.
and achieve what you want to do directly from that.
Same location.
Yeah, I see.
But I do get the information directly from the relay.
Yeah, but I think this is more, because these days, every relay has a PMU.
Every relay has a
Yeah.
PMU.
So I think your question is valid. I think it's effectively the same.
Yeah.
Yeah.
Okay, sure, thanks.
Well,
And
one of
yeah,
the, go ahead.
So this is kind of a different kind of topic. I'm curious about your market optimization algorithm when it comes to including DERs and the microgrids in the greater market. So kind of a couple of shorter questions. First one being, do you take into account the DERs being a significant portion of the grid? As in, do you consider your actions to have an effect on marginal prices throughout the day?
In the future, yes, absolutely.
But I mean, as of right now in your algorithm.
As of right now, that's sort of noise, but as more and more penetration and more market participation is starting to happen in Australia, so I see it's going to happen here. It's going to be a major influence on the pricing.
Yeah, no, absolutely. I actually just did a poster presentation where one of my graphs showcased why it's important to communicate that. And so my other curiosity was what factors do you take into optimizing? Yeah, it sounded like you were saying you were doing the 5-minute intervals, so really working with the real-time market.
If there are questions on the remote attendees, please post them on the chat. We have maybe a couple of more minutes before we get to lunch. Yeah, go ahead.
Yeah. So I was mostly just curious, what all do you take into account? What kind of information do you want as a DER operator in order to, as best you can, participate in the market?
Okay, I can give you the exact schema that's used in Australia. Every DER signs up with an aggregator. The aggregator then makes a bid every 5 minutes for its portfolio. The bids include a range of buy and sell prices and volumes. This is sort of new to me. I had not seen this before, but they give you a price and a volume for buying and selling, and they call them a boffer, B-O-F-F-E-R. Okay, so a boffer is made by the aggregator to the marketplace every 5 minutes during the day. And there are some other rules about when you have to get it in and so forth. And if you make a change, you can make a change, but you can't change the price. There's rules like that. So our software will collect this data from all the aggregators and then calculate a dispatch back to the operator of not the individual commands, but the bulk command that the aggregator proposed. The aggregator then has the freedom to disaggregate those dispatches to maximize his profit,
Mm-hmm.
and then he dispatches. We, though, as the market, read what the individual DER did. to see, did he match what his original bid was?
Hmm.
So there's checks and balances on how this works. And also, the distribution system operator is part of the market as well. Every 5 minutes, the distribution operator sends the dynamic operating envelopes to the market of all of the aggregators that the distribution operator is responsible for. And so this market operates at 5-minute intervals, and it's been operating now for several years. It took us several years to get it developed because the market inventors in Australia didn't know exactly what they wanted. It went through several iterations, hundreds of iterations actually, but it's a pretty sophisticated approach now.
Okay. And then just a final quick one. In that system, are these DERs participating in the day ahead planning?
Yes,
Okay,
yes, real time and day ahead.
great. Thank you.
Yeah, I think we should thank the speaker. Get your lunches and continue the conversation with Dr. Wells. I had one question, Chuck.